Imagine two identical crashes. In the first, a steering motor control wire snaps, sending the vehicle off the road. In the second, every piece of hardware and software functions flawlessly, but the vehicle still crashes because the camera's dynamic range couldn't perceive a pedestrian walking out of a heavy shadow. For decades, the automotive industry relied on the ISO 26262 functional safety standard. That framework ensures a system is safe if it operates exactly as designed, free of electrical shorts, severed wires, or software loops. It solves the broken wire, but leaves the heavy shadow unaddressed. Autonomous vehicles operate in an open world, facing an infinite permutation of environmental variables, weather anomalies, and geographic edge cases. Hardware reliability alone cannot navigate this complexity. To manage the physics of the external environment, the industry developed ISO 21448, known as SOTIF, Safety of the Intended Functionality. SOTIF establishes a crucial distinction. A malfunction is an internal failure, like the severed circuit. A functional insufficiency is an external limitation. The LiDAR sensor reading the fog bank hasn't broken. Its physical capacity to perceive the world has been reached. The SOTIF matrix divides the operational world into 4 areas, categorized by how safe a scenario is and whether the engineering team is aware the scenario exists. Area 1 represents the known safe domain, proven to handle the environment. Area 2 is the known unsafe domain, conditions the system cannot handle, like dense snow. These represent domains an engineer can initially control. Clause 5 of the SOTIF standard dictates the functional and system specifications. Its purpose is to draw a precise mathematical boundary between these safe and unsafe known domains. Autonomy requires deriving system specifications from raw physics to systematically eliminate the unknown. The engineering definition of safe must evolve from preventing internal hardware faults to actively bounding the physics of the external world. At the microscopic level, the physical properties of environmental particles in the atmosphere directly dictate an autonomous system's core capabilities. Clause 5 requires identifying exact triggering conditions, environmental inputs that force a sensor into functional insufficiency. Automotive LiDAR typically pulses infrared light at 905 or 1550 nanometers. This creates a vulnerability. A water droplet size in dense fog aligns with these wavelengths. This causes scattering. The water droplets absorb and scatter the light, creating an attenuation penalty that can exceed 100 decibels per kilometer. The sensor loses visibility due to atmospheric physics, not a software bug. Radar avoids the fog problem, but is vulnerable to complex geometric structures like tunnels. When signals bounce off walls before returning to the sensor, the geometry tricks the system into plotting a ghost target, a vehicle the radar insists exists outside the physical tunnel walls. If the system interprets this data as a stationary vehicle ahead, it triggers phantom braking at highway speeds, creating a major collision hazard. Phantom braking and LiDAR blindness are physical realities that dictate how engineers draft Clause 5 system specifications. Qualitative limits, like do not operate in heavy rain, are mathematically insufficient for functional safety. They provide no hard logic for the architecture to evaluate. Engineers use the Carbonneau rain attenuation model to mathematically bound the weather, where alpha is the attenuation penalty and r is the rainfall rate. In a 50 mm per hour rain rate, the LiDAR's maximum detection range shrinks from 150 meters to exactly 80. This physical limitation collides with regulatory mandates, specifically UN Regulation 157 for Level 3 systems. UNR 157 calculates minimum detection range using braking distance plus reaction time. At 130 kilometers per hour, the regulation strictly demands 144 meters of sight. But the heavy rain limits the sensor to 80 meters. Crossing this mathematical threshold marks a SOTIF boundary violation. Architects manage this by writing strict alert limits and time-to-alert thresholds into the specifications to disable the system before the boundary is crossed. The Target Integrity Risk, or TIR, quantifies acceptable risk to a probability of one failure in 10 million hours. Vague, subjective environmental descriptions are completely replaced by these rigid mathematical formulas in order to deploy a truly verifiable autonomous architecture in the real world. The human element of SOTIF is found in Clause 4's concept of foreseeable misuse. Historically, drivers abused assisted systems by wedging water bottles or oranges into steering wheels to trick torque-based sensors into believing a human was still in control. SOTIF analysis of this foreseeable misuse forced an industry-wide shift to capacitive steering wheels, requiring electrical skin contact to verify engagement. Cognitive misuse is the next target, with Euro NCAP 2026 mandates aiming to regulate driver attention. Safety assessors categorize distraction into two types: the full head owl movement and the eye-only lizard movement. This lizard gaze behavior is mathematically flagged as deep cognitive distraction, requiring the system to immediately initiate a minimum risk maneuver. To prevent mode confusion, OEMs use HMI design, like the turquoise lighting in the Mercedes-Benz Drive Pilot, to clearly signal when the machine has control. A complete SOTF specification applies the same strictness to human cognitive failure as it does to atmospheric scattering. If Clause 5 specifies the knowns, how do engineers discover and map Area 3, the unknown unsafes? A three-pillars verification architecture solves this statistical challenge. To begin, Pillar 1 utilizes strictly controlled physical track testing to faithfully recreate these extreme, known unsafe edge cases. Pillar 2 uses Monte Carlo simulation with phenomenological models that replicate true sensor physics rather than simple kinematics. Pillar 3 involves massive-scale fleet operation using shadow mode data harvesting. The system harvests mismatches, instances where the AI's intent differs from the driver's action, to uncover unknown edge cases. Edge cases from Pillar 3 are converted into knowns, parameterized, and fed back into Pillar 2 simulations to fortify the system. Deep learning perception modules remain a black box risk that cannot be entirely verified. The final failsafe is a deterministic safety guard, which actively calculates physical braking limits in real time to override AI hallucinations. SOTIF operates as a mathematical loop, continuously converting environmental variables into bounded, verifiable safety.